My name is Narasimhan, and on behalf of the Water Resources Center Archives, it is my great pleasure to invite you all and welcome you all for this talk today, the third in the series of 4 talks for this semester. And actually today is a little bit of an aberration in the sense that we usually have our seminars on the second Tuesday of each month. That's what we have decided. For 4 years we have successfully done it, and we hope we will do it in the future. The second Tuesday of each month, whenever the semester is in session. That is how we have arranged ourselves. But this particular month, because of quirk of circumstances, the second Tuesday happened to be a holiday, so we are having it on the third Tuesday. This is a little bit of an unusual thing. Anyway, we have a very interesting presentation today, and I invite Professor Matt Condolf from the School of Environmental Design to introduce our speaker today. The way we have organized ourselves is that we have a committee of people from around the campus who look around and look for good speakers to invite. And Matt Condolf, since the inception, he has been on the committee to help us invite good speakers. And today he is the person who is invited, today's speaker, and I invite Matt Condolf to introduce him.
Thanks, Nari, and thanks to Nari and Linda for organizing the series. Those of you who were here in October for the talk by Thomas Levy, that talk was called A Paranoid's View of the Colorado River. And actually I had something else I had to go to that evening. I came and I thought I would just stay for 15 or 20 minutes, but it was so riveting I wound up staying the whole time and going late to the next thing. But we were going to stick to the Colorado River theme with another paranoid's view of the Colorado River. Jack Schmidt talking about channel change on the Colorado River, a mandate for restoration. Jack is a geomorphologist at Utah State and the Department of Aquatic, Watershed, and Earth Resources and the College of Natural Resources. He has an active research program on the Colorado River and the Grand Canyon for 20 years now. And for the last 10 years or so, he's been working on other rivers in the basin, including a big research program on the Green. He plays a significant role as a scientist and science advisor to government agencies on issues relating to the Colorado River and especially restoration. He was one of the planners and instigators of the flood pulse that was released in 1996 on the Colorado River and collected a lot of data during that experimental flow. It's a pleasure to have Jack here, and thanks for coming.
Well, I want to thank you for coming, and I can't tell you what a privilege it is to have a chance to come here to UC Berkeley. It's a great institution. I want to talk today about the Colorado River Basin and provide an overview of 3 issues. An overview on the history of environmental change in the basin. I want to focus on the current status of our efforts in river restoration and rehabilitation in the Grand Canyon, and then I want to close with some broader remarks about its implications for the whole basin. I'm going to take a basin-wide perspective this evening. Oh. Okay, thanks. California obviously has a intimate and long relationship with the Colorado River. Even though the state of California is a very tiny part of the overall Colorado River Basin, the state of California, even if it only used its compact allotment of 4.4 million acre feet, would be the largest consumer of Colorado River water. And therefore, California plays a very important role in the future of the Colorado River. And so the relationship between the Colorado River and California is an intimate one. Some people cynically view the entire network of reservoirs and dams and diversions as a construct to deliver water to Los Angeles. When I talk to my students in a water policy class, they begin that class knowing that California is the enemy, knowing that Los Angeles is the evil empire of the interests of the river. The issue I'm going to talk about today is whether this plumbing system ought to be, and how we're in the business right now of restoring this plumbing system to its natural characteristics. Because after all, this little section of pipe right here is Grand Canyon National Park. And this junction right here is Canyonlands National Park. And this junction right here is Dinosaur National Monument, some of the great scenic wonders of the United States. John Wesley Powell wrote that the general course of the river is from north to south and from great altitudes to the level of the sea. Thus it runs from the land of snow to the land of sun. And because it runs from the land of snow to the land of sun, it brings snowmelt down to desert areas badly in need of that water to fuel urban growth and agriculture. Charlie Hunt wrote in the late 1960s that the river crosses great structural barriers. And the crossing of great structural barriers and the crossing of the river across a great expanse of the Colorado Plateau gives the river an abundant number of sites to build dams. And so running from snow to sun in a landscape where building dams is a relatively easy, is a possible enterprise has led to the substantial development of the basin. The natural hydrology of the Colorado River is a snowmelt-driven hydrology. Here I've plotted the mean daily discharge for 1952, a year before the closure of dams in the upper basin, that shows the annual hydrograph from October to the next September 30th, and shows the rise and shows the snowmelt pulse of water moving through the basin from the headwaters of the Green River, here at the very top of the watershed at the edge of the Wind River Range, all the way through to the middle of the Grand Canyon down here. And you can see that the river's flow, even in the Grand Canyon, was dominated by this pulse of water moving through, which is the snowmelt domain from the mountains. I took the available hydrologic data and constructed this map in which the width of all these traces of river courses is proportional to the mean annual flow and the mean annual sediment load of the river. And all these nodes that are the small streams of the Rocky Mountains and the central plateaus of Utah are the source of most of the water that flows through the system. And the width of this bar, the mean annual flow of the river, does not significantly change. So the amount of water that is available for diversion by the state of California has its origin in the Rocky Mountains of the upper basin states. As has been often observed as long ago as the 1960s, the sources of sediment to the Colorado River system that gives its name is a different geographic distribution than is the geography of where the water comes from. The water comes from the edges of the basin. The sediment primarily comes from the middle of the basin. If you look at the proportional width of the San Juan River in terms of its annual sediment load and its annual water flux, you can see that this relatively small upper basin tributary delivers a substantial amount of sediment to the river system, much more than is its proportional contribution of water. And so we have a river system, water coming from the edges, crossing the dry country, adding fine sediment in the middle of the basin. The significance of that is that the environmental impact of dams is different if the dam is built along the edges of the basin where it controls the water flux, but the sediment flux continues to come in downstream from the dam, versus a dam such as Glen Canyon that controls both the water flux and the sediment flux. Now, this annual hydrograph, again, for pre-dam years prior to the closure of Hoover Dam, illustrates the fact that between the time that the water enters at Lee's Ferry and crosses into Mexico, again, the hydrology of the river is essentially driven by what comes out of the Rocky Mountains far upstream. In this sense, California cares greatly what goes on in the upper basin. Historical accounts of the lower river along the Arizona-California border describe a circuitous channel, generally shallow, at low flow, and one of constantly shifting channels, banks, and islands. The fabulously biologically productive delta of the Colorado River in Mexico was described by Aldo Leopold. And at high flow, during the high flow season, the lower Colorado River was navigable by steamboats as far north as the confluence of the Virgin and the Colorado River. Within Grand Canyon, the dominant world that John Wesley Powell explored and that subsequent adventurers explored was a fairly stark world of emergent sandbars next to a turbid stream with a small riparian community, a river that was seasonally cold with ice cover along its margins in winter, warm, greater than 16 degrees centigrade in summer, and a river generally devoid of riparian vegetation. This is Frederick Dellenbaugh, a photograph taken during the second Powell expedition, sitting at the mouth of Lador Canyon in extreme northwestern Colorado. The riparian band is more extensive, and here it's box elder, Acer negundo, but again, a river with big emergent sandbars and some distinctive topographies that we know now play a role in the life history of some of the endemic fishery. The perspective on the future of this river has changed substantially. In 1946, the Department of the Interior wrote, "Yesterday the Colorado River was a natural menace. Unharnessed, it tore through deserts, flooded fields, and ravaged villages. It drained the water from the mountains and plains, rushed it through sun-baked, thirsty lands, and dumped it into the Pacific Ocean, a treasure lost forever. Man was on the defensive. He sat helplessly by to watch the Colorado River waste itself, or attempted in vain to halt its destruction. Today, this mighty river is recognized as a national resource. It is a life giver, a power producer, a great constructive force. And we should not forget the mindset of public good that drove the construction of dams in the basin. The first dam that spanned the Colorado River itself was a small dam in 1909 to facilitate the establishment of irrigation diversions in the lower Colorado River near Yuma. And the construction of dams since that time gradually added storage to the basin, but then the tremendous increase in storage with the construction of Hoover Dam in the mid-1930s. Today, Lake Mead Reservoir remains the largest reservoir in the United States. After that, there were completions of other dams in the lower and upper basin, completion of dams downstream of Hoover Dam, and then with a great phase of construction of dams in the upper basin, with the completion of the dams of the Colorado River Storage Project, the total basin storage increased such that the total reservoir storage in the entire basin today is more than 6 times the mean annual flow of the river. No other drainage basin in North America has such a high proportion of reservoir storage to main channel flow. The bulk of this storage is Lake Powell. The remainder of it is Flaming Gorge and some of the other reservoirs. The implications of reservoir construction and diversions is to generally add to the ongoing total consumptive use by off-stream diversions and trans-basin diversions represented by this green line, and the countervailing trend is a decreasing flow passing the international border to Mexico, such that in most years this line is simply the 1.5 million acre-feet required by the 1944 treaty. The changes in hydrology are widespread throughout the basin. In blue on each of these plots is a mean annual hydrograph for the years between 1923 and 1935, a set of years when there are lots of old gauging records. And in yellow is a mean annual hydrograph for the period 1967 to 2000. This substantial drop in flow of a small headwater of the headwaters of the Colorado River is due to the fact that most of this water is shunted off in tunnels underneath the Continental Divide and sent to Fort Collins and Denver and the Colorado Front Range. This is a comparison of those two time periods for the Green River at Warren Bridge coming out of the Wind River Range in Wyoming, where there are no trans-basin diversions. And these are the hydrographs of the most downstream gauging stations on the upper Colorado River, the San Juan River, and then the Green River. The upper Colorado River is subject to both the construction of large dams that tends to reduce the magnitude of the annual flood and increase the magnitude of the base flows during the rest of the year. But this is a system also subject to substantial trans-basin diversions underneath the Continental Divide to the Colorado Front Range. So there's an overall decrease in stream flow as well. In contrast, the Green River coming out of Wyoming is not significantly diverted at all. And therefore, the mean annual flow for these two periods is about the same. And so the main effect is simply dams reducing the magnitude of floods, increasing the magnitude of the base flows. On the San Juan River, there's both trans-basin diversions and dams. So again, it's a combination of effects. So the transformation of the hydrology of the river is widespread. Let me focus now on the work that, briefly on the work that we've undertaken in reconstructing the history of environmental change caused by dams below Flaming Gorge Dam and Lake Powell and Glen Canyon Dam, the largest and second largest reservoirs of the upper basin. We all know that dams induce a number of changes to the water and sediment flux. Trapping of sediment behind dams, not below dams, behind dams, and the creation of higher base flows tend to induce erosion in the downstream channel. The reduction in the magnitude of floods and the continued influx of tributary sediment tend to induce deposition. And it's a relative balance of these changes and these changes that creates different sediment budgets downstream from dams. And we now recognize that immediately downstream from dams, we have reaches that are in sediment deficit, and then further downstream, with a continued influx of tributary sediments, we have sediment surplus reaches. Now, when you build a dam at the exterior margin of the basin, you're only really controlling the water flux, because the sediment flux is still pouring in downstream. And so what we've learned below Flaming Gorge Dam is that the sediment deficit reach is relatively short, and most of the river is in sediment surplus. Ned Andrews of the USGS pointed this out in 1986, and our work has simply revised the lengths of the segments based on more extensive analysis, but such that the sediment deficit reach is about this long. There's a reach in sort of sediment equilibrium about this long, and the rest of the river, its problem is too much sediment. In contrast, we now realize that essentially the entire Grand Canyon, 240 miles of river, is in sediment deficit. So the kind of environmental issues and the kind of issues that we're faced with river restoration are different in a river that's accumulating sediment versus a river that's in sediment deficit. So let's look at the changes downstream from Flaming Gorge. These are the time series of the annual instantaneous maximum discharge for the gauging station immediately downstream from the dam and at Green River, Utah, at the furthest downstream end of the dam. The time series go back to the early 1890s, and we've reconstructed that record at the station immediately below Flaming Gorge Dam. The first thing we've learned is that we really need to subdivide the hydrologic history of the 20th century into 3 parts, not 2. This change is a change represented by the closure of dams and the completion of the Colorado River Storage Project. But we also know that there was a shift from a very wet hydrology at the turn of the century to the hydrology of the Dust Bowl in the 30s and the 40s. And it's important to recognize this, because if we hold dams responsible for change, and we're trying to reverse that change by reoperating dams, we need to understand whether we're trying to return the river to a hydrology that existed immediately before closure of dam, or a hydrology that existed further and longer ago. And we do have photography back to this era. But return to this hydrology, known now to be the wettest in 500 years based on dendrohydrologic work, is a goal which would be impossible to meet. Now, immediately below the dam, the effect of the dam is the greatest, a 60% reduction in the magnitude of the 2-year recurrence flood. But because the Green River also includes the Yampa River, a wild, unregulated tributary coming out of northwestern Colorado, the hydrology of the rest of the river is a combination of a truly regulated dam-controlled system coming out of the north with an unregulated system coming out of Colorado, such that the magnitude of the decrease of floods at Green River, Utah is only about 20% decrease versus 60%. And so this is a close-up of the upper part of the Green with the Yampa coming in. We have a gauging station at just downstream from this confluence, and we've reworked the sediment budgets for this reach. Prior to the dam, about 50% of the sediment came down the Yampa, 50% came out of Wyoming. Now, of the total sediment passing Jensen, about 95% comes out of the Yampa River. The sediment flux in this reach of the river has decreased by about 90%. If we look in the sediment deficit reach immediately downstream from Flaming Gorge Dam, we see that in some places, eddy sandbars have been completely evacuated, similar to what we see in the Grand Canyon. We also see the establishment of vegetation on active channel deposits elsewhere, such as on this gravel bar or debris fan in the foreground. But the channel bed has not changed at all. This is the time series of thalweg elevation at the gauging station downstream from the dam, and including the period prior to construction of the dam. And we've seen no change in bed elevation. That's because the reach immediately below the dam is coarse-bedded, debris fan-dominated rapids and riffles. Further downstream in Browns Park, our sediment budgets indicate that the river is not in deficit. It might even be in surplus. We really can't say, so I'll call it a sediment equilibrium reach. And this is a match of a photograph taken before 1920 with its match today, a substantial narrowing of the channel. And we've reoccupied old abandoned cableways established at before 1920, and the bed elevations are no different today, even in the sand and gravel bedded reach of Browns Park. This is a match of that Frederick Dellenbaugh photo taken in the canyon of Lador in Dinosaur National Monument. A narrowing of the channel, overgrowing of the channel by native and non-native riparian vegetation, and so a substantial transformation from aquatic habitats to terrestrial habitats. Elsewhere in Dinosaur Monument, we've had the conversion of gravel bars to floodplain environments where gravel bars now are overtopped by fine sediment and become part of the floodplain. We've lost aquatic habitat that we know to be of importance to spawning for some of the endangered endemic fish. Ironically, this sort of setting, overgrown former flood gravel bars now become floodplain, is the setting for invasion by a federally threatened orchid, Spiranthes divoluus. I can't say I forget the species, but a federally threatened orchid, Ute ladies' tresses orchid. And so even with transformation, we've got a shift in habitats for aquatic and terrestrial species, all of which are of special concern to land managers. Now let's look downstream at Green River, Utah, at the edge of the southern edge of the Book Cliffs. These are photo matches from prior to 1920 and matches today. You can see a line of cottonwoods at the edge of the former floodplain. Today, only a few matriarchs left along the edge of what has now become a terrace with inset surfaces dominated by other riparian vegetation. We've resurveyed cross-sections originally surveyed before 1920 and in 1928, and what we see is an inset deposit with two lower surfaces that suggest inset floodplain development below what had been the floodplain of that very wet cycle of the turn of the century to a terrace surface of the hydrology of the middle of the century to a surface adjusted to the hydrology since closure of Flaming Gorge Dam. And by looking at the USGS cableway measurements at the active cableway at Green River and measuring the bankfull channel width, we can develop a temporally rich signature of channel adjustment through time, which shows a period of adjustment immediately following the completion of this cableway, the establishment of essentially an equilibrium channel width that lasted for nearly 20 years, and then an ongoing channel narrowing since closure of Flaming Gorge Dam. These data of mean channel width are temporally poor. There's only a few measurements, but they're spatially rich data because they represent GIS coverages developed from historical air photos for about a 25-mile reach of river. And the pattern of these data fits the temporal pattern of the cableway measurements and gives us confidence that the conclusions apply to a relatively long reach of river. Channel narrowing brings with it habitat simplification. These are former islands in the middle of the Green River with secondary channels behind them. Today, those secondary channels are have all but disappeared, and these former aquatic habitats have now become part of the new floodplain of the river. Below Glen Canyon Dam, the problem is too little sediment, not too much. The transformation of the hydrology of the river has been profound. These are instantaneous discharge data developed by David Topping of the USGS, and this black swaths after completion of the dam represents the daily cycle of hydroelectric power generation, only broken by the wet years of the 1980s and the 1996 controlled flood. If we sort of average that hydrology and calculate the average mean daily discharge and compare a pre-dam period with a post-dam period, again, the changes in the hydrology are profound. But what we've learned in Grand Canyon, primarily by the work of Topping and his colleagues, is that these base flows still are higher than the base flows that would retain fine sediment in Grand Canyon. And so when fine sediment comes into Grand Canyon, it moves through. I'll come back to that. But the issue here is that reduction in flood capacity, although great, is matched by a 98% reduction in the sediment supply. That's evidenced in this plot, in which the width of these arrows is proportional to the mean annual sediment load before and after closure of Glen Canyon Dam. There's been a 98 to 99% reduction in the sediment flux through Grand Canyon. The tiny amount of sediment that comes out of the Paria River is too small in relationship to the magnitude of those base flows now that exist in Grand Canyon, such that they're able to effectively move even the small amounts of fine sediment through the system. The result has been substantial degradation of the channel. In the 15 miles of river immediately downstream from Glen Canyon Dam, the river has degraded as much as 5 meters. This is a plot which we developed of the Thalweg elevation going down the channel for 15 miles as it existed in 1956. And this contact between sand and gravel is the contact that was identified by the Bureau of Reclamation in its borings drilled into the channel bed in the 1950s. The blue represents the elevation of the bed today. Not only has there been significant degradation, not only has there been degradation of pools and riffles, but we've transformed the river from a sand-bedded river to a gravel-bedded river. And that brings with it changes in the riverine ecosystem. At the same time that the channel has degraded, there has not been significant change in channel width. We developed a GIS based on historical air photos for the entire reach between the dam and Lee's Ferry. In areas of purple are areas that were sandbars that have now become gravel bars along the river. And in red are areas that have eroded where there's been channel widening. But in green are all areas that were sandbars that are now overgrown by riparian vegetation, are perched above the channel, and are now an abandoned terrace of what used to be an active bar. And the net result when you calculate the active channel width of the reach is that it's actually narrowed. So in Glen Canyon, the channel has degraded and narrowed slightly. In the Grand Canyon, the bed has not changed its elevation at all. Why? Because the bed is held up by coarse boulders of the debris flows that come into the river and create the rapids that create the famous whitewater experience of Grand Canyon. So the degradation or the channel change in Grand Canyon is not one of bed elevation change, it's one of evacuation of sand out of eddies, as represented in this match photography from the 1950s and the 1990s, in which eddy sandbars are now gone from the edges of the river. This eddy sandbar here remains, but it's been deflated and is about 2 meters lower than it was prior to the dam. There's high variability in the characteristics of these sandbars. This represents a sequence of air photos at a site in the middle of Marble Canyon back to the 1930s, when you may be able to see a large emergent sandbar. Large sandbars, although this flow is very high in 52 and 56, and today almost nothing left of that sand. We've had to come up with ways to define metrics that could be tracked through time. Just suffice it to say for this talk that we built complex and involved GIS databases, nested all of these data, tracked the changes in size and distribution of sandbars, so we could develop a really, truly spatially rich database with which to understand sandbar change in Grand Canyon. Let me take a minute to just point out some things that have happened downstream from Hoover Dam along the California border. Not that I do any work here, but I think it's an important piece of the puzzle. This represents a transformation of the hydrology of the Colorado River below Davis Dam. Prior to construction of Hoover Dam, after construction of Hoover Dam. But most significantly, the change of the hydrology at the international border, in which the average hydrology of the river is simply the average flow, such that the total area under this curve is 1.5 million acre feet. At the same time, Hoover Dam completely traps all the sediment that comes in below Glen Canyon Dam. This, in fact, is old data prior to the closure of Glen, showing the suspended sediment load of the station in Grand Canyon, essentially the sediment load entering Lake Mead and the sediment load below Lake Mead. The difference between this was the sediment captured in Lake Mead. These numbers then got much smaller after closure of Glen Canyon Dam. But again, it's a clear water release below Hoover Dam. So the result of complete dewatering of the system and trapping of sediment has essentially been to turn the lower Colorado River from a river that was navigable by boats at high flow to a small channel that more resembles an irrigation canal. And it truly represents an irrigation canal in the 240 miles that have been leveed and channelized. So the transformation of the river is profound downstream from Hoover Dam. Now what I want to talk to is efforts to reverse this. The first thing is that the efforts to reverse these conditions are substantial and need to be paid attention to. They're the stuff that funds the research of numerous faculty members at higher education institutions. They fund the degrees of many master's and PhD students around the West and around the United States. But more importantly, they have the potential to affect the distribution of water and electricity in this country, and we need to understand it. The Grand Canyon Adaptive Management Program is one of a number of programs focused on different parts of the basin. The Upper Colorado River Endangered Species Recovery Plan, the San Juan River Endangered Species Recovery Plan, the Lower Colorado River Multi-Species Recovery Plan, a plan for the Virgin River. The environmental communities focus now on restoring the Colorado River Delta. The environmental communities focus on decommissioning Glen Canyon Dam. Efforts to change the water allocation strategy for the state of California. We have a whole host of different efforts underway to reverse the present environmental condition of the Colorado River. Before I talk about those efforts, I want to remind us that part of what river management is sometimes relatively little science and relatively little negotiation. And if it wasn't for the strong stand of some people on some issues and a refusal to negotiate, a place like Echo Park and Dinosaur Monument would now be underneath a reservoir, and a dam would exist right here in Marble Canyon, the Marble Canyon Dam site. But sometimes you do negotiate, and now we live in a world where adaptive management and stakeholder-driven adaptive management programs is a paradigm we're all used to and we're all used to working in. I want to talk about the Grand Canyon Adaptive Management Program because one of the votes in that management program is the vote of the state of California. So in a convoluted sense, you send a vote to determine the fate of how the Colorado River in Grand Canyon is managed, along with representatives of environmental groups, recreation groups, Native American tribes, and traditional water users. The management goals for the Grand Canyon Adaptive Management Program are a mixed bag. It's a conflicting set of messages. One is the message of the Colorado River Storage Project Act, passed in 1956, which was the act that authorized the construction of the large dams of the Upper Basin. These uses are very traditional uses. But the Grand Canyon Protection Act, signed by the first George Bush president, stated that another objective of dam management was to protect and mitigate adverse impacts to and improve the values for which Grand Canyon National Park was established. Well, the mission of the National Park System is to preserve unimpaired the natural and cultural resources and values for the future enjoyment of this and future generations. And this mission are inconsistent. In the stakeholder-based world that we live in, although we might wish for a simple set of river resource objectives, we've ended up with a complex set of resource objectives. I would submit that a problem with stakeholder-based decision processes is the effort to keep everybody at the table happy. And because of that, we end up with a set of resource objectives that say restore populations of extirpated species and maintain a wild reproducing population of rainbow trout introduced to the system. Maintain flow dynamics and sediment storage in the system, and yet maintain power production capacity. There are conflicts here. And some of my colleagues and I, several years ago, suggested that meeting all these objectives is nearly impossible, because some objectives of river management fit under a category that we called relics of the pre-dam river. And if you want to restore these attributes of the river, well, then you need to recreate the pre-dam water and sediment flux. But if you want to maintain these attributes of the river, these attributes of the rivers are artifacts of the post-dam water and sediment flux. And to some extent, the Grand Canyon Adaptive Management Program is caught in a web of trying to meet all objectives. I just want to hit on a few items of interest in understanding the physical system of Grand Canyon. During the 1996 flood, when the hydrographs remained steady at 45,000 cubic feet per second for 7 days, the concentration of sediment in transport in the river, measured at various gauging stations near the dam and further downstream, precipitously decreased and halved over the time frame of the flood. Subsequent experiments run in the late 1990s during other spike flow experiments show severe depletion of the system very quickly. This began to send signals to us that the river did not accumulate fine sediment over long periods of time. It quickly ran out of sediment. We learned from that, and I'm bypassing a large array of work by a number of people, that realizing what severe sediment deficit the Colorado River and Grand Canyon is in. Now, since the 1996 flood, there have been a number of other test flows. We've constrained the range of operations. We've had periods when the flows were very low. There's been a substantial effort to change the flow regime. We've developed complex decision processes, hydrographs that look as complex as this. Hydrographs intended to allow for influx of fine sediment, turn the river off, put a spike flood, redistribute the fine sediment to the edges of the river, real-time measuring of fine sediment budgets, decision matrices in which geomorphic data is downloaded and analyzed in weeks of time and presented to stakeholder groups to decide whether spike flows should occur or not, but all based on accepting the existing sediment supply system in which we essentially have 1 or 2% of the original flux left to work with. We've learned that most of the sand today is stored in eddies in a relatively small amount of the river channel, and that when we run a flood, if we do not, when the flood begins to run out of fine sediment, then after that point, we basically are mining the eddies out of sand. So we've learned that the eddies, which are the place we're trying to have be the sediment sink, the place where we aggrade sediment deposits, also runs the risk of being the source of the sediment if we don't have enough sediment in the charged system. This is a map developed from bathymetric data in which we've compared the bed topography in August and September before and the net result of a spike flow in which we got pods of significant bed erosion of more than a meter during a particular prospective flood. And then this is the channel bed change in the next 2 years during a period of sustained low flow. And if we go back and forth, you can see that the areas that were scoured by the flood are the areas where we have aggradation subsequent to that. If we look at a larger spatial scale of the places where floods are able to evacuate temporarily stored fine sediment, and then where it degrades 2 years later, you can see that we basically keep flip-flopping in the locations of where we store sediment and where we accumulate sediment. It's over a relatively small part of the river channel. So how are we doing? How are we doing in managing the river over the last several years in manipulating flow? Well, this is a sediment mass balance for fine sediment between 1999 and 2003. And this represents a calculated cumulative fine sediment budget for the river, for the total river system above the Little Colorado River over a 4-year period. These are the error bars of this calculation. If we started at 0, we are today in deficit. 4 years of carefully manipulating the river to hold sediment in the system has accomplished losing fine sediment out of the system. How have we done at restoring and improving the area of sandbars along the river? This is a time series of the cumulative volume, the average volume of sand at usable elevations for campsites in Upper Marble Canyon from 1990 to 2003. Despite the aggradational event of 1996, today's sandbars in Upper Marble Canyon are much smaller than they were when we started in 1990. This is a plot for sand lower down in eddies. Again, you can see that in fact, for all monitoring reaches, today we have less total sand stored in eddies than we did in 1990. For all of the cost and manipulation of flow, we have less sand today than when we started this adaptive management program in Grand Canyon. We appear to be losing the battle. We appear to be losing the battle of manipulating flow when 99% of the sediment is behind Lake Powell. The question before us in scientific terms is it possible to reverse the long-term loss of sand from the system? Not only has there been this big change from pre-dam to post-dam, but even in the last 10 to 13 years of careful adaptive management, we're losing the battle even further. If not successful, how much more sand than that naturally supplied by the Paria River is going to be necessary to reverse these degradational trends? Or do we need to announce to the American public that the irreversible price paid for the construction of Glen Canyon Dam is a progressive deterioration of the environment of Grand Canyon? The choice of returning a river from some present condition to some other state, whether it's to go all the way back to truly wild or to go part way, is not a decision of science. It's a decision of public policy. Our job as scientists is to spell this out, no matter how difficult it is to tell that story. In the Colorado River Basin, the Grand Canyon Adaptive Management Program is only one of many programs. And those programs are not linked merely because they're in a watershed. They're linked because they're linked in an electricity distribution system. And the prices paid in lost hydropower in Grand Canyon are often made up by changes in operations in some other dam. So we have to think about things on a much bigger scale. We need to not only tell the story of how a river changes, such as evidenced in this line that I'm pointing to, that I've called an environmental change function, this graph of decreasing flood flows in the Platte River and a narrowing channel offered by Gar Williams in the 1970s. We tracked the time sequence of the history of channel change, and I've told some of that story for the Colorado River today. But now we need to understand what it takes to drive the system back the other way. And the ability to drive a system back the other way is one of performing field experiments and adaptive management to learn what in the world the shape of reversal of environmental trends is all about. And certainly in the case of the Green River, with a narrow channel and abundant riparian vegetation, you just don't add water to the system and expect the channel to re-widen. because now the channel is completely armored by tamarisk. So what we need to be doing in the Grand Canyon and what we need to be doing in every river restoration program in the basin is define these restoration response functions. We need to define x-axes, which essentially are things like how much water, how big should the prescriptive flood flows be? Should we add sediment to the system? An axis which defines doing a little and doing a lot, costing a little, costing a lot, taking a long time to implement, taking a short time to implement. Things that are politically risky, things that are politically easy. And as scientists, we need to define which environmental changes, whether it's restoration of sandbars or restoration of endemic fish or restoration of native riparian forest, for which restoration activities is a small amount of cost get us lots of improvement versus a small amount of cost get us not much improvement. Because if we have this, and if we define this for different parts of the river, then we can define which parts of the river we might want to concentrate our efforts. So I ask you to think about issues like, are we trying to protect relic resources or artifact resources or both? Should we in fact try to really rehabilitate every segment of the Colorado River Basin to the same degree? Should we pursue, could we ever pursue the intense effort that we pursue in Grand Canyon everywhere else? Or should we in fact look at the whole basin, define restoration response functions, and perhaps focus our efforts on reaches that have experienced less environmental change than in Grand Canyon? Or perhaps we ought to be focusing on the sediment surplus reaches and not the sediment deficit reaches. Or maybe we shouldn't be pursuing much of anything down here. This all matters to the state of California. In one sense, the state of California doesn't care about any of this, so long as the water comes down here. The biggest opponent to flood releases in Grand Canyon is the state of Colorado. Why? Because the state of Colorado wants more water to go this way. The state of Colorado doesn't want the precedent established of environmental restoration flows going this way. The state of California says, hey, it's still coming our way. What do we care? The state of California, however, will care tremendously if we ever pursue a similar restoration program for the California Delta in Mexico. And so the geographic position of California actually puts it in a very powerful position. Because in a sense, as I tell my students, the endangered fish of the upper basin never had as great a friend as Los Angeles. Because all Los Angeles cares about is that water stays in the river, and that's what fish care about. So you have a position of power in this basin that actually is going to be in alliance with many of the environmental concerns of the upper basin, but certainly not an alliance of the lower basin. Thanks.
Any questions? Yeah.
I couldn't resist. You made a mention about what science must do. But science itself is in a sense divided, because in sciences we have the physical sciences and we have natural sciences and biological sciences. What you are now talking about comes from the earth sciences and the natural sciences. Because the systems are so complicated and so interlinked that it's difficult to control them, it's difficult to precisely measure them and characterize them. Yet we have, on the other side, based on the physical sciences, the whole world is going on the stock market, everybody wants 7%, 10% real growth for another 100 years. Everybody wants to become rich. There ain't no way you can compromise the needs of these rivers, and maintaining them, restoring them is going to place very severe restrictions on how much resources we have to drive our economic growth, which we are thinking about. And so even in the scientific community, if you take the physical sciences and the natural sciences, or the earth sciences, the biological sciences, we have a tremendous conflict. We think that physical sciences, given all the research that goes on in physical sciences, we can solve all the world problem, we can have a continuous growth. This says that the earth is a finite system, we cannot possibly do that. Just a comment.
Here's one thing we could do. The state of Utah is never going to divert water out of the Green River. Flaming Gorge Dam produces 10% of the power that's produced at a Glen Canyon dam. All 4 endangered species, federally endangered species in the entire river system, live in the Green River, as well as elsewhere. The highest, the Republican governor of Utah, now the head of the EPA, once proposed that we market this water to Las Vegas and downstream users. The rest of the upper basin went ballistic, mostly the state of Colorado, and so it never went anywhere. In my mind, if you remove this large dam and this absolutely worthless dam called Fontenelle in Wyoming, you would restore a fully wild hydrology and sediment flux to the Green River. You would not compromise the water delivery or hydroelectric power system. You wouldn't compromise the water delivery system at all. You'd compromise the power production system only to the degree of 10% reduction. I mean, that's not a trivial amount, but it's nothing like removal of this dam. To me, we ought to be looking for the opportunities in the basin where we can get some parts of the system back to a wild system and still recognize that the highest and best use of the water is its diversion down here. Right now, I'm sort of conveniently ignoring the plight of the Delta. But I'm saying that the opportunities for restoration here, but meeting the needs down here are not, they are not at odds. They're not at odds with the needs of Las Vegas. They're not at odds down here. This is not the Rio Grande system, which is about as impossible a river basin as I can think of to try to offer a vision of hope for. But I can at least envision a wild green river system, which is the refuge of the endangered fish. And we will have depletions out of the Grand River Division or the Upper Colorado. We will have some depletions out of San Juan. But maybe our ecological friends will tell us that we ought to get the complete restoration of some parts of the basin in exchange for perhaps not trying here, if the same species, rather than improving everything a little bit, maybe we ought to have more courage and go for everything in a few places. That's about the only thing that I can suggest.
I had a question about the test flows that the Bureau of Reclamation did in the early 1990s. What was the theory and the purpose of those flows, and what did that test actually achieve?
It's an involved story which some of us have told and I have written about. If one takes the sediment, a standard sediment rating curve for the various gauges of the Grand Canyon region, and looks at what we expect to be the scatter in those relationships, about a log cycle, and draws one line through the middle of that cloud, as we usually do, and calculates a sediment budget for each gauging station based on drawing a line through the cloud of data, and then multiplies those data times mean daily discharge data, one calculates a sediment budget for the Colorado River that indicates that the Grand Canyon can accumulate fine sediment during normal power plant operations, and it can sustain that accumulation for nearly a decade. So the hypothesis of the flood of '96 was that Grand Canyon accumulated fine sediment for many years at a time, essentially like a bank account. We accumulated all this fine sediment on the bed. A flood, perhaps once every decade, would then redistribute that bank account sediment up to the margins of the channel, and then the rest would go to Lake Mead. That was the hypothesis, or that was the mindset we had. What we learned was the reverse. We learned that the flood ran out of sediment in about 2 days. We learned that only because of the flood. The flood, those curves, looking at the steep declines in concentration, in many ways was the most important finding out of the flood, because it led some researchers to go back to the historical records and look more carefully and realize that sediment transport in Grand Canyon is dependent on how much fine sediment is actually temporarily on the bed. And when you have a big flush of fine sediment into the channel, the sediment transport rates are elevated, they're very high, and then you quickly deplete the system. So we learned that the system cannot retain fine sediment for long periods of time. Our view now is that the system only retains fine sediment on the order of days to weeks, not decades. So we've learned from the flood the severe limitation of storage. So what did we accomplish? The biggest thing that happened was that the biggest thing about the 1996 flood was it happened at all. It was a political statement that there was a commitment to try to manage the river. So it was a demonstration project. The demonstration didn't actually work all that well, because the lasting influence of the flood has only been a couple years. We knew that sand would be redistributed from the channel bed to the channel margins. We knew that would happen. The question were rates, amounts. But the greatest thing about the flood was the scientific learning. We fundamentally changed some of our thinking about sediment transport, the variability of deposition from one part of the canyon to the other, and we learned an awful lot. It's been a very painful lesson, because although we talk about adaptive management, stakeholders work very hard to cut political agreements and political deals that take years to negotiate. And when they finally developed the negotiations and changes in the annual operating plan for the dam, they thought they had it. I mean, that's what adaptive management is. What they didn't expect was that the scientists would change their mind about how the river worked. And that's been the biggest thing, is that suddenly we have, oh no, we were wrong, the river works differently. And the political side of the issues is, hold it, we cut all the deals. It's in the EIS, it's in the record of decision. What do you mean adaptive management doesn't mean scientists change their minds? And that's exactly what happened. And so that's where we're struggling now. What I talked about sediment deficit, my colleagues and I wrote about in EOS in May of 2002. It's been in memos for longer than that. The political system is only barely being able to respond to that now. The biggest time for fine sediment recharge to the Colorado River is in October during the monsoon season. The very best time to run a prescriptive flood is immediately after that occurs. But traditional interpretation of the law of the river says that any high flow releases can only occur between January and June during what is administratively called the flood control season. So the upper basin states, namely the state of Colorado, say you can run a flood. It's got to be in the first half of the year, because then we don't run the risk of a precedent that this is going to become something annually that has to go on in delivering water from the upper basin to the lower basin. What that means is a prescriptive flood can't occur until after January 1st. And so the traditional water community would rather have, and they agreed to, turning the river off, base loading the power plant for 3 months, stopping the production of hydroelectric power for essentially 3 months to stall the movement of sediment by dropping the flow so low so as not to set a precedent of sending water from the upper basin to the lower basin. And so if the Paria River had flooded this fall, which it didn't, I would have spent Christmas and New Year's in the bottom of the Grand Canyon. Because we wouldn't have run it at the right time, because it conflicted with this traditional interpretation of the law of the river.
I get the impression that the lakes immediately upstream of every dam is a bank for sediment. Why not change the hydraulics so that the water comes out of the bottom, taking the sediment with it and clearing out those banks?
Please do so.
Would that work?
Absolutely. That's all we need. All we need is to get the sediment from behind. What we need, the solution to the problem is a sediment in Lake Powell. Absolutely. And we don't even need all of it, given the altered flow regime. But we need something more than nothing. Now in India, in the Alps, in China, there are bypasses of fine sediment. And these are built into the structures. Even in 3 gorges on the Yangtze, it's going to have to be dealt with. The problem at Glen Canyon is that the reservoir is 160 miles long. And as with any prograding delta, all the sediment and all the sand is 100 miles away at the other end of the reservoir. And so the dilemma is how you move fine sediment 100 miles to the dam, and then how you get it around the dam. Emmett Larson, a well-known engineering professor at the University of Arizona, had a student work on some of this 20 years ago. To all the engineers in this room, please figure this problem out. That is the solution.
In California, we have an issue with the Sacramento-San Joaquin system, as you probably know, that also has large stakeholder groups and a large multi-agency entity dealing with it called CalFed. One of the things that's sort of taking hold now is to try to scale down some of the rivers where the sediment is trapped and the water's trapped, and to see if a self-sustaining ecosystem can function. Your experience with the '96 release indicates that that doesn't seem like that approach worked in the Grand Canyon. But I wonder, do you think there's other parts of the system upstream, perhaps, that could work with a scaled down water and sediment supply, resulting in a self-sustained system?
Well, what I'd submit is this. I think that the issue of a scaled down system is a relevant question for sediment surplus reaches. In sediment deficit reaches, where just the place is continuing to be stripped out, so it's continuing to change. But in the upper basin, that's a very relevant question for restoration ecology. Does the Green River in Dinosaur National Monument, which is now sort of adjusted as a much smaller system, but it now essentially has a channel capacity to move the sediment, the tiny amount of sediment that comes in through. We're not getting much more progressive narrowing of the channel there. Is that scaled down little river just the same as the bigger river? It has proportionally more floodplain environment, proportionally less aquatic environment. By my take, I'm not an ecologist, I think the place has lost all the spawning bars that the endemic fish used to use. So to me, it doesn't look like it's the same deal. And to me, it still looks like a bad deal. But that's where I'd ask that question. The same issue has been asked even on the Rio Grande between Fort Quitman, Texas and Presidio, where the river is about as big as you could put 1 foot in Mexico and 1 foot in the United States. The river's got a little adjusted channel. It's now got a floodplain. You could even find Bankful Stage if you wanted to. It's got a huge riparian valley. I've actually heard people that I thought were sane people say it's just fine. It's in adjustment. To me, it seems nuts. But I've heard rational people argue it the other way. I think it's a very relevant question. I have no idea what the answer is. I think you turn to the ecologists amongst us.
What's the current thinking about the lifespan of the major reservoirs on the Colorado?
Well, the bad news is the current thinking is it's still many hundreds of years. And since the United States is only 200 years old, whether Lake Powell has 300 years left or 500 years left, I think we will make important public policy decisions about the future of those dams before we're forced to. I think as a society we'll make courageous decisions about those futures before our hand is forced. I suspect that Southern California and Central Arizona will decide that the water loss by evaporation and bank storage is too important to lose. That would probably be the most important driving force to ever decommission the dam if it were decommissioned. I frankly don't think it ever will be decommissioned. I just think the constituency for that place is just too overwhelming. I think the constituencies in support of other dams is much less, and we ought to be going after decommissioning of other things rather than the second largest reservoir in the United States. But my friends in the Glen Canyon Institute passionately disagree.
I hope you'll give a little plug to your beautiful book, and especially if it's still in print. But I do have a question.
Michael, the picture book?
Yeah, well, the one with all the beautiful pictures.
Yeah, Michael Collier, a good friend and a wonderful pilot and photographer, took a Earth, Wind, and no, not Earth, Wind, and Fire. That's a. I can't even remember. What is the name of the book? Earth, Water, and Earth and. But it's a book. It's by University of Utah Press. Wonderful pictures of the Colorado River Basin. A number of us wrote chapters in it. Thanks.
Well, I wanted to ask you about this quotation you had, the U.S. Department of Interior, 1946. Yeah. It's hard to beat this. Yesterday, the Colorado River was a natural menace, and American engineering's turned it into a lifesaver.
Yes.
It's hard to beat that idea, and I think when we have a historical perspective on this basin that's 150 years deep, this myth sounds fairly accurate. And it seemed like part of shaping public policy is coming up with a deeper sense of the history of the Colorado River Basin. There was a whole civilization that inhabited this basin before our own, and inhabited it from a millennium and more. They just had agriculture, they just had industry, they just had urbanization. It just happened to be a different kind of civilization. And much of our thinking about the Colorado River Basin is based on this American 150, it's 155 years since 1848. That's all we know about the Colorado River and its basin. And somehow it seems like to affect public policy, you have to somehow gain a truer sense of the history and the true definition of this river. Is it right just to call it a natural menace and we're converting it into a life giver? That's not a full that's not its full story. And, you know, it leaves us with, for example, considering that the Colorado River Delta is in Mexico. No, the Colorado River Delta goes to Palm Springs, California. The whole Salton Trough is part of the Colorado River Delta, and the only reason we can consider the Delta to be in Mexico is because we've engineered to cut off water flow into the whole Delta. Well, you know, it's just like we're looking at this narrow historical slice, and I don't think, I'm glad there is so much natural science being conducted, but there's some, you know, this watershed and water system are serving a civilization. And until we get a sense of what, you know, what's deeper than our own civilization and, you know, to give us more of a sense of what the future might be, I think we're kind of locked into this ideological statement that the Department of Interior wrote out. It's hard to beat turning a natural menace into a life giver. That's hard to beat.
And the Colorado River isn't alone in that. I mean, the Rio Grande is a classic transformation. The Rio Grande was a big, constantly shifting river, impossible to live along. But lots of people lived along it before it was the United States and Mexico.
I guess I have a two-part question. The first part is, does writing off the decommissioning of Glen Canyon Dam as politically impossible contribute to making it impossible? And does it seem to you desirable to decommission Glen Canyon Dam if it could be done?
Well, I am a passionate river runner by hobby. I only do this work because, I mean, I'm blessed that I do what I do, and it's also what I love to do. I guess that as a matter of public policy, I don't think it's a wise thing that the first big dam we would take down would be the second largest in the United States. I mean, I do honestly think that we ought to get it right a few other places first. I mean, I'm not the least bit afraid to decommission the Elwha Dam in Washington. I'm not the least bit afraid to consider decommissioning dams in the lower Snake River because I'm convinced by reading and listening to colleagues about its impact on the salmon fishery. I do very honestly mean that I think the best public policy decision is to make the Green River a wild river system. I think it's consistent with the vast infrastructure needs of the basin. And I guess that, and I will say that the people who lead that campaign are close personal friends of mine. And I do know that that it is part of the puzzle, that if you say it's impossible, then you make it a little more impossible. But I'm just a college professor and I have to express my opinion. And so my opinion is it's not the wisest campaign. But am I going to tell those people to stop campaigning for that? No. Am I going to say that they shouldn't wage that fight? No. But that's just my opinion. Now, should it come down? Well, I mean, that'd be pretty serious business to take that dam down. That's an awful lot of sediment there. We'd have to draw the reservoir down quite slowly so that we didn't completely overwhelm Grand Canyon with fine sediment. We'd need to study the reservoir sediments and look at potential geochemical transformations. But I mean, I proposed doing that study to the Bureau of Reclamation this past summer because the reservoir is low and they refused to fund it. So I'm not afraid to study those questions, and the Bureau is afraid to study them. It's not a bad thing. I mean, I certainly dream of imagining myself floating in a boat through Glen Canyon. It would be a wonderful thing. But I guess I'm being honest. I just know how hard it is to get dams decommissioned right now. And I guess I would pick some battles that I thought were more winnable. But if you choose to wage the fight and be part of that effort, I will only congratulate you.
Let's thank Jack again for